Hmm. Welcome to Doc Waller's Earth and Space Report for Friday, May 26th, 2023. I'm your host, Bill Waller, an astronomer, science educator, and communicator, coming to you on a cool and clear spring evening in my hometown of Rockport, Massachusetts. These Earth and Space reports are intended to engage and inform people like you who are curious about Earth as a planet, who care about our life-sustaining environments, and who wonder about the greater cosmos and all that it contains. Video recordings of these reports are archived on the Earth and Space Reports YouTube channel. They are also in regular rotation on the 1623 Studios Community Access Cable Television channel. I'm grateful for the continuing interest and support shown by Rockport educators and students, Cape Ann cultural colleagues, cohorts of the Gloucester Area Astronomy Club, sundry Earth and space scientists and communicators, far-flung friends, family, and other curious folk. Thank you for your active participation and encouragements. This evening, I will discuss advancing Earth and space exploration in our schools. This presentation has a more educational focus than most of the prior presentations in this series. Indeed, it is a call to action for us to integrate Earth and space science education as a vital part of our K-12 school curricula. So without any further introductions, let's get going. So I'm going to share the screen. And we're going to share, boom. And then I'm going to go to the presentation. And I'm going to do the slideshow from the beginning. Okay, so this one slide pretty much tells it all. It's that we live on a moist, living planet where land meets water. I guess it's a lake in a national park, and we have an atmosphere, and then we also have a magnetosphere, which was then very active with an aurora, and then beyond that, this particular photograph captured a comet. That was Comet Neowise, which occurred during the height of the pandemic in June or July, as I recall. We got to see it. And then a background of stars. And all that is a part of our visceral existence. It's called Earth and Space. So currently, the Earth and space sciences are often taught separately. And sometimes they're hardly ever taught. So I'll move you guys over so you can see this picture. And so what are the Earth and space sciences? I asked this question. And it's, again, you can see it here. There's all sorts of wonderful things happening here on Earth. These things are called hoodoos, which are products of erosional processes here on Earth, weathering processes on Earth. And these regions are particularly stubborn, these towers, to the erosive process. And so pretty cool. And then in the background is a setting sun. I believe this is a planet right here. And then beyond, the greater Milky Way. What a fabulous photo. So let's just talk about what we're dealing with here. In the earth sciences, it's the study of Earth's geosphere, the rocky stuff, hydrosphere, the wet stuff, cryosphere, the frozen stuff, atmosphere, the gassy stuff, biosphere, living stuff, and all their evolving interrelations. It's in many ways intuitive for us because we have evolved. We are products of evolution that have transpired over 3.5 billion years on this particular planet. Now, the space sciences considers Earth again, but as a planet, one of several in our solar system. And then, of course, other stellar and planetary systems, which we're now learning more and more about. The Milky Way galaxy, our home galaxy, which you can see in this long exposure image. Other galaxies, and the large-scale cosmos, its structure, origin, and evolution. So I would contend that they all really comprise one integrated subject that's important to learn about in an educational setting. So this idea of teaching about the Earth and space goes back a long ways. You can go back to 1893, where there was this report of the Committee on Secondary School Studies of the National Education Association. And I'm going to move you guys over to the left-hand side so you can see this. I'll put you right here. You begin with physics and chemistry, which are regarded as the physical sciences. And they have it here in the third year, chemistry and physics. So that hasn't changed. Maybe when it is taught has changed. Astronomy was actually recommended in the second year. And then there was this thing called, what was it? Physical geography. And here you have meteorology, geology, or physiography. These were all courses or topics that were recommended in the fourth year. I would also like to note that what was also recommended was a whole lot of Latin and Greek and rhetoric. These are courses which are rarely taught these days in secondary school systems. So these are the underpinnings that go way back when in the United States. Today, we have the next generation science standards, which came out, I can't remember when they came out, to tell you the truth. And they basically espouse three main sciences that should be taught across the K through 12 grade spans. First, there's the physical science, which would include both physics and chemistry. Then there's life sciences, which we would otherwise know as biology, and then maybe environmental science as well. And then right up there, high priority, Earth and space science, which has a fair bit of astronomy here, and then the rest is Earth science, okay? So this is what is recommended across the grade spans at the national level in the United States. We'll move on. Individual states have gone on to embellish this or create details. Here is basically a progressive sequence from pre-K through second grade all the way to the 9th and 10th grades at least. And this is just in Earth and space science. So there's a progression which just begins with what you can observe, patterns of motion of the moon and sun. That's age appropriate. And then by the time you get to the 9th and the 10th grade, you're trying to explain things according to some theories, like tectonic theory, for why continental rocks are older than rocks of the ocean floor, et cetera. And that there's feedback effects among the various Earth systems. And so this is all recommended that it should be taught. It should be part of the curricula. So why even bother? Well, there's this little photochemical experiment that's very much underway across our home planet, and that is the global warming that we've been experiencing over the past 150 years, since around 1880s. And you can see that just on average, things are starting to get a little hot. And that has led to the generic climate change, which you hear about all the time. But the major origin of the climate change is global warming. And we have pretty much settled on a cause for it. and it's that the Earth's atmosphere contains gases which block the re-radiation from the warmed Earth in the infrared. They block that infrared radiation, which cranks up the temperature. It traps that radiation. And we are fortunate to have these trace gases of carbon dioxide, methane. Oh, there you go. Carbon dioxide, methane, and nitric oxide. These are all greenhouse gases, as is water vapor in the clear gaseous form, not in clouds. And we're fortunate to have it because it has kept Earth moist, though the water's mostly in liquid form for much of the history of Earth. But what's been happening is that we have been upping the amounts of these trace greenhouse gases through our industrial processes, combustion in particular, and that has increased this greenhouse effect, so that carbon dioxide alone is up by more than 44%. We're nearing, a 50% increase in carbon dioxide. Just that alone has led to some significant warming of Earth by more than 1 degree centigrade, which I think is like 1.8 degrees Fahrenheit. So this is a major experiment that we're doing, and it's a quintessential Earth and space science topic because it involves the sun interacting with the Earth and its atmosphere. Who better to teach this phenomenon than an Earth and space scientist? Then there's just the story of the universe going back 13.8 billion years and following the transformation of matter from particles to stars and galaxies, planets around the stars, and the chemical evolution that had already started in the star forming clouds, but then continues on the surfaces and in the waters of the planets. And at least on one particularly moist planet, we got biological evolution, cultural evolution, and techno evolution. So this greatest story of all is, again, a quintessential Earth and space sciences topic. It's the natural home for telling this story, the greatest story ever told. Then there's the fact that people notice the fact that they are on a planet, and they go to special places on the planet, our national parks, to enjoy what is there, these magnificent geological features, and then in many of the parks, fabulous skies where you can even see the Milky Way. Back in cities, there are magnificent planetariums which attract millions of people as well to the shows that they can experience. And these are very immersive shows over a dome. And with the new digital projectors, there's a lot of fabulous animation, which allows explanations to be even more vivid. Then there's just the iconic images. And these are images that you grew up with, beginning with the image of Earth as seen from the moon. They call it Earthrise, but it was actually the orbiting spacecraft that made the Earth appear to rise. But nevertheless, this was a fabulous image showing a whole hemisphere of the Earth, well, in gibbous phase. And to think that all of our joys and triumphs and miseries are just located somewhere on this little planet. It's just amazing. There's a very precious planet. And then another iconic image taken with the Hubble Space Telescope were the so-called Pillars of Creation. It's part of the Eagle Nebula, Messier 16. And you can see all the wonderful interactions at play here. Some stars above the field of view shining down and actually creating celestial hoodoos through their photoevaporative processes. And there's these little lumps here, which are exposed star-forming cores, which are getting photoablated. It's not clear whether they will survive this action, but it's a beautiful, beautiful image. And then there's the Hubble Ultra Deep Field, which you probably heard about. I can tell you what in this image is a star. This is a star. This is a star. And I think that's a star. And everything else is a galaxy. And they can see galaxies upon galaxies that go way back in distance and corresponding light travel time. So some of these little red turds at the edge of infinity here are galaxies being seen in their youth around 13 or 10 billion years ago. I think that's how far the Hubble Ultra Deep Field goes. And this sort of image, and now the follow-up with the James Webb Space Telescope, have truly transformed public consciousness, that we are delicate creatures on a fragile planet living in a vast cosmos that extends in space and time more than you can ever fathom. Also at museums, not just planetariums, but you can go and visit celestial objects. This is the Willamette meteorite, is arguably the largest meteorite that has ever been collected. It's at the American Museum of Natural History. And then, sorry, go back. And this is the lunar lander next to, I think, help me out, you guys. Lucky Lindy. I think this is Lucky Lindy's plane. And this is the first. This might be the Gemini capsule, and this might be the Mercury capsule, and this is a Mars lander. These are all very popular artifacts that people can go see and learn about. It just shows just how much public interest there is in what's come to Earth and what's now out in space. And as far as education is concerned, Earth and space science relates to STEAM education: science, technology, engineering, arts, and maths. And you can see that here with what happened in 1972 with the deployment of the Apollo 16 mission. Not only did they land on the moon and able to go and venture forth in a pressurized spacesuit, but they built a rover that could scoot along the lunar surface with communications already there. And then in this particular mission, they deployed the first ultraviolet telescope, the first telescope ever to be deployed on the surface of the moon. Excuse me. And this particular telescope, gold-plated, successfully imaged nebulae in our own galaxy and nearby galaxies as well. So we know it can be done, and we're planning to do it again soon. But that's a lot of STEM right there: science, technology, engineering, and math. And then here's an example of the arts. This is just realistic art, realism. It's an artist's conception of the Mars Perseverance rover on the surface of Mars. I guess that would be the Jezero crater. And this is the implement that is drilling into various rocks and getting samples, which are getting cached and left on the Mars surface for subsequent missions to pick up and bring home. So this is an artist's conception, but there's a lot of ways in which artists can engage with these topics. So I just want to read these. You've got in situ and remote sensing, spacefaring, how do you ever get there? Telecommunications, big data, visualizations, which would be something like this, robotics, and human factors. How are you ever going to keep these humans alive? So that's the case for studying the Earth and space sciences, and yet there's very few opportunities to teach high school Earth and space sciences. And this I compiled in 2020. It's the number of job opportunities. There is a particular website for teacher job opportunities, schoolspring.org, I believe. And so these were the openings at that time. Biology leads the list, but also chemistry and physics are high. And then way down are the Earth and space sciences. So if you train as an Earth and space scientist educator, you don't have that many opportunities. And so that just is telling you that it's not getting taught. It's getting under-taught, despite the mandates and the interest. So that's the job market. And then there are the issues, which have been quoted by several folks. More than any other secondary school science, Earth science is contextually homeless. And other stats at the high school level, you have about 72% of Earth science teachers certified to teach the Earth science. So that's not so bad at the high school level. You know, if they have the courses to teach, there's a majority of teachers who have some sort of qualification. At the middle school level, which is things are worse, where most Earth science courses are taught, less than 20% of Earth science teachers majored in an Earth science area. And typically they are majors in other sciences, science education or elementary education. So that comes from the National Association of Geoscience Teachers, but it gets worse. Overall, only 40% of all Earth science teachers have ever taken a single course in these sciences. Okay, so the lack of expertise is embarrassing. This is an old quote. I'm just hoping that it's gotten better. But there's no motivation as far as I can see. And some reason for this lack of teaching Earth science in particular, and lack of teaching it integrated with space science, is that astronomy typically is taught at the college level in physics departments, okay? It is rarely coupled with the Earth sciences. The departments don't get together. Contrary to the K through 12 expectations and recommendations, here you have a listing of astronomy-related departments in the directory of the American Astronomical Society, and most of the departments are physics departments. And then half again are combined physics and astronomy departments, like Tufts. Tufts is a physics and astronomy department. I taught there. I taught astronomy. Then there's some standalone astronomy departments. And then way down here are Earth and space science departments, and even lower Earth science departments. So the integration is just not there. And if you want to find somebody who can teach astronomy, you're more likely to find that person in a physics department. So we have a major call to action. You have to grow lungs, grow feet, learn to walk this year for sure. But these are the various things that you need to do. You need to identify and coordinate the institutional stakeholders in the Earth and space sciences. Get them talking together. Establish integrated degree programs in the Earth and space sciences at our colleges and universities, especially with education routes. Because the mandates exist and the interest exists, and we should be responding to it. And then for catch-up, you should be developing professional certificate courses and workshops in the Earth and space sciences. And given that physics departments have a lot of astronomy in them, you can encourage high school physics teachers to take on Earth and space science instruction. And that was done in my high school when I was teaching, and continues there with the person who has replaced me. He is teaching not only physics, but he's teaching astronomy elective and most recently an earth science elective. So it can happen. Or you could hire an actual earth and space science educator. I mean, that would be the optimal thing. So I gave this pitch at a meeting of the American Association of Physics Teachers, and these two gals came up to me afterwards, and they said, you're not going to get anywhere until they increase the number of required science courses from 3 to 4. That would do it. But of course, that's a budgetary issue. And so in the meantime, I think maybe encouraging physics teachers to teach the Earth and space science is the way to go. Okay, so that's pretty much my pitch. I'll reiterate, but in the meantime, I can just show you an example sequence, curriculum sequence for the earth sciences. So you can imagine a 2-semester high school course beginning with the earth sciences. You could call it earth system science. And this thing just writes itself. This curriculum just writes itself. You just think about Earth as a planet, the basic physics of it, shape, size, mass, density, and how you can infer the internal structure of it, how we spin, how we orbit, how the sun irradiates our surface and causes it to warm, the interior structure based on earthquakes and seismic soundings. We've learned the core mantle crust layers. Also, we've learned about the magnetism of Earth, which indicates a magnetic component to the core. So these are all things that can be figured out in a geophysical manner. The crustal structure and dynamics, you can start with the basic elements and turn them into molecules, which make up minerals, rocks, and then the rock cycle, which involves tectonic activity, and the consequences of volcanoes and earthquakes. And that's just the crustal structure. The surface waters, which includes the hydrosphere, the wet stuff, and the cryosphere, the frozen stuff. That's certainly worth addressing. Then there's the atmospheric structure and dynamics. It's such a thin part of our overall planet, but you can learn a lot by monitoring the temperature in the atmosphere, temperature profile, as well as the pressure, the densities, and the winds, and how they are governed by the pressure systems, low and high pressure systems, and the thermal gradients from the equator to the poles. And that leads to weather and climate, and how, for the latter, that has been affected by human influence. And finally, the sun-earth connection, how not only the sunlight affects us, but solar particles affect us, and those particles interact with our magnetosphere, which shields most of the particles. But when the sun gets particularly active, we can have geomagnetic storms and technological consequences, such as blackouts and corrosion of pipelines and all sorts of other stuff. There's books available in the Earth and Space Sciences. This one's particularly targeted for the next generation science standards. I like this book a lot. It's an integrated science textbook, but you can just select the chapters to suit your needs. Beginning with the Earth, or we're beginning with the basic Big Bang, if you wish, to build the elements, and then you move on to building stars and planets, and then you can get into Earth's structure. Here's an Earth science course, and then this is a physical science course with Earth science. So that kind of underscores the fact that a lot of Earth science can be understood in a physical way through the lens of physical science. And then the next semester, space science, you can consider the Earth-Moon system, how we mutually orbit our center of mass, and how the moon raises tides on the Earth, the cratering history on the moon, which leads to surface ages and the origin and evolution. Of course, we have hunks of the moon that we've brought back and analyzed, so that's why we know the moon is as old as it is, 4.5 billion years old, and that there's parts of the moon which are younger because of early volcanism. And then move on beyond the Earth-Moon system to the solar system. That's a book that is going to follow my astronomy book, which is focuses on the solar system. And of course, people have an interest in the solar system because it's our home system. And then moving out to other stars and their various physical properties, which allow us to determine masses, how they're powered, and how old they are, and how they got born and how they evolve over time, and what's left over, either white dwarfs, neutron stars, and black holes. You got to have black holes, otherwise the kids will disown you. Exoplanetary systems, which is a new field. The Milky Way galaxy, which is our home galaxy of stars and nebulae, star clusters, and dark matter. And it has an origin story as well, 12 billion years old history. And then moving on out, galaxy systems, out to the cosmic web, and how the galaxies are all expanding away from one another as space is literally expanding. And then finally, cosmic evolution. I can't read this, but it's basically, following what's going on in the universe over time. How galaxies get made, and an enigmatic role of dark energy. We don't know. I can strongly recommend, in addition to my own little book, this book. This is a free online textbook by OpenStax. I help with some of the chapters. And then the Khan Academy has a good cosmology and astronomy textbook that is very pedagogical. It's full of questions and ways to correct yourself in terms of your thought processes. And then you can also, teachers can be guided by the Big Ideas in Astronomy that was put together by the International Astronomical Union. So that's the sort of thing that could occur in a high school. And also you could organize introductory college courses this way. There are degree programs in the Earth and Space Sciences at various universities. And in addition to them, many schools basically have you major in an Earth or space science, and then you take the additional educational courses to qualify you as a teacher. So there are existing degree programs, which I'm happy to note. There's also certification workshops, certification courses and workshops that are available through NASA and the American Geophysical Union, International Astronomical Union, the National Association of Geoscience Teachers, and especially in astronomy, the Astronomical Society of the Pacific. So there are organizations that are associations that are stepping up to the plate at the back end for the for certification courses and workshops. But the state boards of education, I think, are going to have to get serious about whether or not they're going to be teaching the Earth and Space Sciences. So this is kind of like my coda conclusions that the next generation science standards do prioritize K through 12 Earth and Space Science instruction. And most state curriculum frameworks mirror this priority, but they're undertaught, especially in high school. Middle school kind of tries to cover everything. But there seems to be a real dearth of Earth and Space Science teaching at the high school level. I recommend that given this dearth of job opportunities and corresponding courses, that physics teachers can step up to the plate to teach the Earth and Space Sciences. They typically teach a 5-course sequence, and they could teach physics for 3 of the courses and advanced placement physics, and then or 4 of the courses, and for the 5th course they could teach either the earth science or the space science. So I proposed an Earth and Space Systems curriculum. It basically just writes itself. Universities could provide Earth and Space Science programs for pre and in-service teachers. And finally, professional societies need to do a better job of proposing and advancing professional development opportunities towards these ends. So I think that's it. Oh, yes. So I'm a member of the U.S. National Astronomy Education Coordinator team, one of 5, and we represent the United States for the International Astronomical Union. And so we have a website, of course, and it provides featured events, including Earth and Space Report recordings, because I tend the website. And but it provides, all kinds of services and funding opportunities as we find them. And you're welcome to interact with us that way. But your feedback is essential. That feedback from those 2 teachers from, I think, Providence, Rhode Island, was very important to me. That we're gonna make minimal headway until more sciences are taught, 4 courses rather than 3 courses. And so this is just, banging the nail with the hammer a little more. Approach your favorite Earth and Space Science organization. Approach your favorite educational institution. And then nurture, what is it, your Earth and Space Science education community. And so I believe that that's it. And yes, that's it. Okay, so I'm going to stop sharing. Wait a second. How do I new share? No, I don't want to share anymore. Stop share. There we go. Okay. And Paul, you have your hand up?
Yeah, I do. I'm wondering whether as you know, Bill, I follow space weather.
Yes.
You didn't mention it, and I can see why, because it's not really a science yet. But I think people are going to become more aware of the influence of space. There's a new science called heliobiology.
Wow.
And the idea, and most of the information so far is anecdotal. So it's not a real science, okay? We don't have data. But there are a lot of people who feel that their bodies respond like during a big solar storm. And
Mhm.
people have debated whether this is really true or it isn't. But now that some people have come with this, some people are trying to get some, empirical data to check on it. But I think that's going to be a big thing if it's true, because it will alert the people to the influence, the between the Earth and the sun and the space. I mean, the other one is that during a minimum, solar storm minimum, it's more dangerous to fly across the Atlantic
Right.
because the cosmic rays are greater. Okay, and during a high max, the Earth is protected by the stronger magnetosphere. So I just wanted to, point that out.
Yeah. I did have it listed in the Earth Science sequence as a Sun-Earth connection.
Yeah, I did see that. That was, but this heliobiology seems to be something, bubbling up. I don't know. I don't think there's any good proof or anything with it. Yeah.
It's something which is hard to monitor because
Yeah, that's the problem. It's very
it's,
tough to monitor it.
it's
Yeah.
health.
Huh?
It's health. It's how it affects people's bodies.
Right. Yeah.
And it's harder to track, but that it sounds like it could be a very worthy thing. As we already know that that radiation is harmful, particle radiation, and
Well, I look at the arguments for like early on, people said secondary smoke. There was no correlation. But when they started looking at it, it got pretty interested,
yeah, that's good. If I was to write the textbook, which I don't think I'm going to, in the earth sciences, maybe I would add that in there right at the end when I could know the maximum amount. So, Bill, you have your hand up as well.
Yeah. Hi, Bill. Hi, everyone. You made a number of really good points there. Well, first, getting back to the question that Paul was asking, and you were talking about heliobiology, and you can't monitor people's health. Well, they have some devices that people wear now, and then they can be connected to some network. So you could have large scale studies of people's health and how they correlate with what's happening in the sun, for people who opt into that, right? So that is a possibility, right?
Neat.
Yeah, I wanted to talk about, you were saying how astronomy, astronomers are either part of the physics department or mostly part of the physics department, and they should be more, connected with Earth and space sciences. I would make a case that it should also be, well, maybe not quite yet, but it's almost time to actually connect them with the life sciences as well, because of what's happening with the exoplanet atmospheres, looking for biosignatures.
Yeah. Exciting times with astrobiology.
Right.
The earth sciences has to include the biosphere as well. We have literally transformed the planet through not our particular life, but even going back further with the microbes and the sea creatures that made the cliffs of Dover.
Exactly. Yeah, that's right. Life affects geology. That's right.
Yes, Mary Ellen.
Hi, wonderful presentation. I thought it was just great. I have a neighbor who's a retired geologist and claims that we're not having climate change. We're just in an interglacial period, which is very annoying, but because of course he's wrong. Humans are contributing to whatever natural periodicity there is going on in nature. But one of the things that intrigued me when I was teaching and trying to combine different sciences and show how everything is connected to everything else. Instead of taking it stepwise or in a top-down fashion among subjects, I chose a concept and then showed how everything connected to that concept or contributed to understanding that concept, so that you could talk about periodicity in nature as a concept, and you could have everything from the Big Bang to, glaciology to, climate change to evolution to the rotation of the planet around its orbit. I mean, everything involves some form of periodicity. It's much harder to teach that way. I think in my case, I had chosen grass and gave a whole semester course just on grass, everything about it, all of its scientific, biological, historical, and linguistic, everything to do, even read poems about grass, so it was an experiment. It was an experiment in education, but the whole point of it was simply to show how everything is connected to everything else.
Right.
So the details of particular fields come out sort of naturally as an aside to try to answer the questions. But I'd be the very first to acknowledge that this is probably impossible to actually apply in public education, to be able to teach that way.
Right. They have their curriculum frameworks that you have to hit. Though you have more freedom in the elective courses, as the ones that don't get tested, like with the Massachusetts, what is it? Massachusetts Comprehensive Assessment System, MCAS. They tend to be in biology or physics. But with electives, you usually have more freedom as a teacher, which is nice. But to center it around a concept, I've kind of walked in backwards with the inverse square law, that how it can be found in so many situations, from the force of gravity to the intensity of light and the
good. All
force of the electric field. Pardon? I'm sorry.
Great minds think alike.
Yeah. I mean, I couldn't believe that it was not an important concept in the physics framework. It was like, oh my God, this applies in so many areas, and it's because we live in a three-dimensional universe, which you could actually conduct an experiment. So I did want to mention that I've only discussed curriculum. I did not discuss pedagogy, but I will say one thing, that especially these days, if you don't have the kids doing something, they're just not going to be engaged.
Right. Good point.
There was a day when you could lecture. Back in the day, I experienced it, but the kids nowadays just don't seem to have the in the high school ages, they don't have that attention span like they used to.
Yeah.
So yes, Yves. You're going to need to get.
Oh yeah, very interesting speech. Thank you. I was thinking. I'm thinking for years to try to inform more high school students and the general population, even on something that is really important to understand: the universe and the climate and Earth, which are models, numerical models done on computers. And my dream is that kids, when they finish high school, would have a general understanding on how these models are functioning, how they are made, why they are made, and what are the data required to make them valid. to estimate the percentage of error and so on.
So I want to
yeah.
ask you what you mean specifically by models, because I use it in multiple ways.
Oh, yeah. Yeah, for example, for climate, you have to build a numerical model to do predictions. And that requires a lot of historical data from all over the planet that you enter in a structural model. The first thing you do is a structure. You create a structure of the Earth in a computer. Then you divide the atmosphere and the oceans and so on in cubes. You give physical properties to these cubes, and then you enter laws linking different parameters. And you make that model go back in time, and you try to match the historical data. And then when it works, you can begin to project what will happen in the future and so on. It's
Predict.
extremely complex. It takes a lot of years of college to be able to do that properly. But it would be nice if people had a basic understanding of what it is.
Mm-hmm.
Yeah.
So these are very complex models. You're talking about meteorological models. There's some of the most complex models that that humans have devised, and so in order to help students understand modeling the actual process, they will need to have examples which they can actually do, to make explanations, maybe either visually or 3D models, literally 3D models that they can hold in their hands. An equation provides a model. That's in my more expansive definition of model, an underlying concept like the periodicity of Mary Ellen's, that the inverse square law is actually a model. It's a way to inform the phenomenon that you're observing, and then you test them, to see whether it works. And I remember doing the test for sound intensity, and it was a little off. It was a little off. It was either the sound one or the light one where we measured the intensity as a function of distance. And so either I could blame it on the fact that there were reflections off of the desk surface, or the size of the light bulb or whatever. But otherwise, I'd have to say we don't live in a three-dimensional universe, which is where you would expect things to fall off as 1 over the distance squared. But your models, those are based on basic physics. They're based on other models, if you will. How the transfer of heat depends on an pre-existing temperature gradient, for example. And then you break it up into cubes because everything's interacting with everything else. So it's a two-way street. You want them to gain an appreciation for what we have learned at the most sophisticated end, but we have to give them an entree for making their own models and making their own explanations, which they'll feel proud about, that they can take ownership.
Okay. You cannot just describe, you have to make them work themselves. Yeah. Okay.
Yeah. So this is we could do a whole other gathering on pedagogy, because I know that many of you have fabulous backgrounds and experience dealing with students and trying to convey the truths that you have learned yourself. So, okay, so I guess it's time. Do we have a comment from your educator in the back, Yves and Michelle?
So, yeah,
I'm assuming that Massachusetts has 3 credits of science required for high school. There'd be biology, chemistry, and physics. Anything
That is
else would be
correct.
an elective. Right, I agree with those other 2 teachers that told you until you get a 4th elective, I mean, a 4th required science,
Yeah.
yeah.
So
It's-
what does that mean? Going to the State House?
Mhm.
Yeah, yeah,
I mean, there is no geology, geography required.
required, no, that's not a requirement,
That's
and it's
very
not.
different.
Well, that's what I'm saying.
So, okay, we can all say here, let's go for a 4th course.
Yeah, well,
I'll sign any petition. I'll sign a petition.
yeah.
Go back to high school.
Yeah, go back to high school, the 4th course. All right, gang. This has been great. And thank you for indulging me on this slightly more educational presentation.
Thank you,
Thank you,
Bill.
Bill.
It's great.
Mhm.
Thank you
Very
very
So will
much.
I see you on Sunday?
Sunday.
Yeah, at the SBY.
Oh, at the yacht club?
Yeah.
Yeah, sure. I'll go get some donuts there. Okay, take care, Paul.
Bye-bye, everybody.
Goodbye. Thank you.
Bye.
Mhm.
Thank you.